Hi everyone, welcome to ST Skills. This is a weekly system design session at Saturday 9 a.m. EST. So the format of this session is like we have a deep dive on one of the system design topics, and this week we are actually doing on Google file system, and we on alternate weeks we do a mock interviews. If you'd like to sign up, so please ping me or like go to sport.stskills.com and you can sign up for yourself using Discord. And so today, like Shia is volunteering to present on Google file system. So with this, like I'll give the forum to Shia.
Hi everyone. So let's start talking about Google file system. So in general, when you think about a file system, what is it? It's um, it's how we read, retrieve, and store the data in a system, a computer system, basically. So if you want to think about it, if you have a single PC, right? And this has some 1 TB hard disk. Whatever files you're thinking about, you can just store it in the hard disk of this PC, right? And how it's going to get retrieved, how it is stored, this all depends on the files system that is being implemented by that operating system, right? In similar way, what happens if your file size grows really large and you cannot accommodate it in one place, right? There the concept of distributed file system comes, where now you need is a lot of storage, where you can keep all your files. So what it will look like is, for example, now you have 100 TBs of data. Now, so basically now you will need, if one system can give you 1 TB, then now you need is 100 similar type of systems, right? And now you want to access the files and store the files, basically data, right? So now what you need is some interface which can help you do that. And that will be our distributed file system that will help us. And Google file system is nothing but a distributed file system. How Google came up with Google file system and why did they need Google file system is because obviously Google being mostly a data company, they had lots and lots of data, in huge amount of data. And they saw a pattern, like what kind of reads and writes Google system generally gets. Like for all the reads, they used to be mostly sequential reads and not random reads. And same applies for the writes. It always used to be sequential writes and not random writes. So they thought like they want to optimize on that, and that's why they came up with the idea of GFS. They wanted to keep the system very simple, and like any complications or like anything that would make system a little complicated, that they left onto the applications that are going to call this GFS system. So they made some assumptions, like they don't wanted to go for, so these hardware, right, they don't wanted to go for some expensive hardware. What they wanted was they should be able to work with the same inexpensive components that they already have in their data centers. And they knew that these inexpensive components are more prone to failures. So they wanted their system to be fault tolerant and identify the failures over in these machines, and to be able to recover from it on its own. So this is what we will see in Google file system. How did they implement all those things? The next thing is, they knew that the files that Google got always were large files. So they always thought of efficiently implementing those large files. And small files were so minimum that they thought even if it is not optimized, it is okay for us to not optimize for small files. And like initially I spoke about the workloads, that most of the workloads, maybe it read or write, it was always mostly sequential. Random reads and random writes were not a common scenario at Google. And that's why what they did, they didn't keep it as an important thing. They didn't think that it was something that they should think about when implementing that and optimize specifically for those small files, right? And the other thing they wanted their system was that concurrently many clients should be able to perform read writes in their machine, uh, to retrieve the data or to write the data basically. So they want, so how they implemented that, that also we are going to see. The other thing is they didn't wanted something like low latency, but mostly they wanted to utilize their entire network bandwidth. So for example, if they wanted to transfer the data between two machines, they would want to um, you know use the entire bandwidth that they could use in order to transfer the whole data there. The other thing important to the design of Google file system is the interface that they provided. So in general, like most file system, they follow POSIX, and this is a standard defined by IEEE, and all the operating system needs to follow that. But Google has organized their files and directories in hierarchy, but they didn't follow POSIX as such. So they had a similar file system interface, but not POSIX. And they provide all the usual operations that any file system provides, like create, read, delete, write, open, close, whatever we do with files basically. Okay, and this is like how the design would look like. So let's see the first architecture of a typical Google file system. So here, um, this is the application and this is the GFS client. This will basically be in one system, like they'll be residing at one place. And this is master. The property of master, it keeps the metadata of all the chunk servers. These are the chunk servers. What chunk servers does is they keep the chunks, and I'll come to what a chunk is in a minute. And these chunk servers all have these Linux file system. So there are advantages on why they chose to go with the Linux system. I'll come to that in a minute. And these are the three basic components. So like whenever you want to implement your own GFS, you need a GFS client, a GFS master, and a GFS chunk server, which are like the central, which are like the center of a GFS cluster. You can also have this where you can run where you can run a GFS client and the chunk server in one machine. But this is not recommended because obviously there could be like resource crunch, because chunk server might have heavy read write requests, and whereas where GFS is calling, it will call chunk server at some point in time, right? So it's not recommended, but you can obviously do that. And for so this is the architecture. So how a normal call would look like is the first call would go to master from GFS client, and probably I can draw and show you better in like steps. So for example, this is my system where my application and GFS client resides. So the first call would always go to master. Not always, like the first time if you're trying to access some chunk server, which information you don't have, you'll go to the master and you ask master that, okay, I have this file and it's the name, and I need to read it, for example, and this is the byte offset. Now master will see like in which of the chunk servers, so it keeps this metadata information, and master sees that, okay, this file name, okay, it belongs to so and so servers, and it responds back to the GFS with the chunk handle that we call. And chunk handle is nothing but, you can understand it as a chunk ID. And then GFS now knows where it needs to read the data from. So the next step is the chunk server. Now GFS will make a call to the chunk server telling him that this is my file name and this is the byte offset, and let me read the data, and then the chunk server will reply with the data that GFS client wanted to read. There is an internal call that happens between application and GFS client. So what actually application sends is a file name and byte offset. What GFS does is it translates this file name and byte offset into file name and index, and that is being sent to master. Basically, not exactly file name and byte offset. It's not given in the architecture as such, but like when you read the paper, they have specifically mentioned this, that how application and GFS client will talk to each other, and then how GFS client is going to talk to the master. So inside this master, what you're seeing is metadata information. And what metadata information master keeps is, it keeps access control list, which is not mentioned here. I have this slide. So it keeps this ACL information. It keeps the version of like the chunk server, because chunk servers are prone to failure. So we must know like which one is the updated one. It keeps the chunk ID, and like it has this file name. So basically this is the hierarchical structure of directory. And then in the file name, each file name has this information like where its chunks are kept, and what is the location of that particular chunk server, and what is the ACL information, and this version, like what is the version that of that particular chunk in the chunk server. So this is depicted by me. This is what I could think of, like it could be could have a table, something like that, and that's how it would be keeping the information. Another information that master keeps is operation log. And what operation logs helps us to do is, if in case the master fails, then we could retrieve the state of master altogether using these operation logs. So these are the components. So GFS client is simple. What they have to do is just have this API implementations of read write. This is what the GFS client is going to do. GFS master's responsibility is to keep the metadata information. Also, it controls some activities like chunk lease management, garbage collection, and chunk migration. And we'll come to that, like what all these activities are and why they are needed. Also, apart from these read write operations, there is some heartbeat activity that keeps on going on between chunk server and the master, because master needs to know like if the chunk is down, and if it needs to rebalance or re-replicate some chunk if the chunk is down. So this is the whole architecture. So I wrote these some takeaways, like what happens. Uh, it's like the similar things that I spoke right now. So if you want, you can just I'll just post this slide in the chat, and then you can just go through it if you want. The other thing is, many of you would be having a question. This master is a single master, and that could be, a bottleneck in this scenario. But it's not that. Why they made a single master is, first reason was they wanted to simplify their design. Another thing is, the only time GFS will call master is when they want to get information about where the chunk lies, right? And apart from that, whatever read and write is going to happen, that is going to happen between GFS client and chunk server. And there will be like hundreds of chunk servers in which data will be replicated. So the single master is basically not a bottleneck. The other important design information is the chunk size. So the chunk size is 64 MB, and this is a fixed size. What happens is if you want to see chunk, it would be something like, for example, these are your chunk servers. And then the chunks would be something inside this. And these all would be of size 64 MB. Another information that master keeps is, it keep like not another, like the same information the master keeps is, it keeps the information of these chunks as well, right? Because these chunks are the one that are mapped with file. So for example, if you had some file, I think I have this example here. So here you have this file, like crawl file, and then whatever the chunks are for this particular file, its IDs are kept like 1 2 3, and then where this chunk location information is available. So for one, the chunk server. Okay, someone has a question, I guess.
Yeah, I'm Tarun. Hi. So, what if a master goes down? If the request is not reaching the response, then what will happen?
Yeah, so there is something called as shadow masters. And what shadow master is, it allows you to perform the read request and nothing apart from that. And there is some a concept called operation logs, um, through which you can reinstate a master. The master information is all kept in memory, and it is persisted at a remote location and to these shadow masters, right? So whenever a master is down for some time, the shadow master does not become a master, but like allows some operation. But there is a possibility that master could go down for like 1 hour or maybe for 1 day, right? Then in that case, a shadow master will become a master.
Okay, thanks.
Yeah, no problem. Uh, so yeah, and this is how like chunk ID is mapped to a chunk server location. And here I have written just one location, but there could be multiple location because of replication that we are going to do. And by default, the replication is configured to be 3, but it is totally user configurable. User can configure it as the way he wants. And we'll see some certain scenarios where we want, replication to be much more than 3. Where the read write request might be very high and it can turn out into be a hotspot. So this, I was talking about these chunk size. Anyone has any questions up till now?
Just have a quick question about the GFS client talking to the chunk server. So
Mm-hmm.
once the client knows the chunk server information from the master,
Mm-hmm.
the GFS client doesn't go and talk to the master again, right? So if
No.
for some reason there is a failure and uh, the GFS client should go to the next backup for that particular chunk server, will it again go back to the master saying that, hey, I am no more able to write or read from this particular chunk you gave before. Give
Mm-hmm.
me the new chunk.
Yeah, it will go to master, because basically it will not be able to reach the client information that was given by the master.
Got it.
Sorry,
Okay.
chunk server information that was given by a master. So yeah, in two cases that will happen. Once, if the cache gets invalidated on the GFS side, because it caches the information of the chunk server. So if that gets invalidated, then it will again have to go to the master. The other scenario is, yeah, if the chunk server fails, it will again go to the master and asks, like, and now I want to read, what should I do?
Got it. One more question about the chunks location for one file. Is there anything around making sure that chunks for one file are located either in one server or overflows to another server to keep things simple, something like that?
I didn't understand overflows to other server.
So, for example, if I have a file which is less than 1 TB, then
Mhm.
the whole file can fit on maybe one chunk server in 64 MB chunk sizes, right? So,
Yeah.
in that case, would there be some optimization, or if at all there is a need for such optimization to keep all the chunks of one file onto one chunk server?
Yeah. So yeah, this is a concept. Sorry. Yeah, this is a concept, and yeah, you're right. It won't be kept in one place because if a file is like a read-write heavy file, then one chunk server will be overloaded.
Hmm.
So yeah, GFS has a way, to identify where it should keep. And even if by chance, right, if it would have kept the entire file in the chunks in one chunk server, what it will do is whenever it will see that, okay, it's a read write heavy, it will rebalance. It will put the some chunks to other, it will migrate those chunks basically.
Makes sense. Makes sense.
So
Thank you. Yeah.
I can talk based off of the my experience with the HDFS, which is based on Google. So what HDFS does is they have two more things in addition to maintaining the chunks. One is called rack awareness. So since they were expecting this to be on a failure-prone machines, you always put the all the three copies of each chunk into the different servers. So always those things will be up. And the second thing was they wanted to keep them as network awareness so that whenever somebody reads the file, they have to have in a same network switch or under a same network switch, so something like that.
Yeah, you're right. Exactly. GFS also does the same thing. So it's a master process where they want to keep the replica, right? Because what you're saying is like if you have one file in one of the machines, then you would want the other replica somewhere a little far. Reason being that specifically in a different rack. For example, if one rack fails, then it should not be like both of your replicas were in the same rack, and now you don't have anything to get the data from. So this is the reason why they put it in a different rack. So you're right. Actually, these are like master processes. It identifies where should I put the replica, and how this re-replication is related to how read-write I was talking about, right? If something is read-write heavy, then how you should re-replicate, or if the node is down, then how you should re-replicate. So these are all master processes. So master runs all these things in background apart from serving the client, and it generally does this when the master is not very busy.
What was the concept of the network awareness on top of the rack awareness?
uh, okay, so for network awareness, I think you can explain better like what you were talking about. I
Yeah,
don't know your name. Yeah.
yeah. So the servers are kept in a rack. Rack we can think of as a cupboard, right? So all these racks, they have all these racks, they have a local router in between them. So that's how they connect in between, and they have something around 100 gigs of connectivity in between them. And then now assume if it's a big data center, there will be multiple racks. Like these cupboards will be multiple, which are each cupboard has multiple servers, and there are multiple racks like that. So there is a global router. I don't know the exact name, but there is a global router which connects all these racks together. But since you are making a global hop inside that data center, which is connecting to different racks, it incurs some latency. So that's what it means. So you want to keep the data, I mean, closer as much as possible. Like you should not keep like two instances here and the third is like in somewhere else in the data center, which is like very far away.
I see. So you're saying the replicas also should be maintaining the proximity for faster access.
Yes, the master does that.
Okay, got it.
Yeah,
Okay.
but I think there is another aspect, right? Sometimes when we replicate, uh, they purposefully keep the replicas in different, data centers or availability zones, because if something were to happen to the rack, right? If we have keeping both replicas on the same rack, then you don't have the replication availability anymore. So for basically for availability, to make sure at least you have one replica available, they usually replicate across different availability zones with different racks on purpose.
Yeah, makes sense.
Yeah.
Yeah. So the first point, like I am pretty sure about. Second one, in fact they said that like one of the examples that Google gave was like how they transfer the data, right? So we'll come to that in later section though, because it will like it will hop a lot, like for me, like because I didn't tell about how read write will happen, but in general what happens in a write, uh, it writes to all the chunk server replicas together. So what happens is it writes to the primary first, and then the secondary, and the next like secondary, all the other secondaries. So that happens is there is a data flow between, and that data flow is between like now network, right? Because from primary the data will go to secondary. So that happens pretty fast, according to like what the paper I read, according to what I read in the paper. And uh, and you would not want like, and you would want your replicas to be in different rack servers. So I didn't read about this latency thing. Probably it's related to
Yeah,
HTTP, but
I think what the previous person was talking about is in Hadoop jobs, right? The
mm-hmm.
processing and the data has to be closer. They have to be in the same rack. If you are
Yeah.
running a Hadoop job, right?
Mm-hmm.
The job is accessing data for your batch offline processing. So the Hadoop makes sure the job is running. Basically, the compute is running in the same rack as where data is residing. So
Yes.
I think from that perspective, yes, they make sure the compute and the storage on the same rack
Uh-huh.
for the
Got
batch
it.
for the batch processing. But from a replication perspective, one of the main criteria is that you don't lose all your replicas, right? So you replicate them across different availability zones and data centers, and you
Mm-hmm.
don't definitely put on the same rack.
Mm-hmm. Yeah, got it. Oh yeah, yeah, you're right. I got it. Mhm.
Okay,
So
one more question from my side.
mhm.
So let's suppose a file is divided into 10 chunks, right? So will master keep all the references of 10 chunks of for a file, or it will just keep a single, I mean, first reference of just chunks and just like offset kind of thing.
No, it
So
will
how
keep
does it go?
references of all 10 chunks. So the metadata, right? It is not
Yeah,
about chunk server. It is about a chunk.
yeah, makes sense. Thank you.
Okay. So yeah, we were talking about the chunk size, and which is 64 MB. So like in a typical file system, when you have a block size, it is around 4 KB, but they decided that they will have 64 MB as the chunk size. And why is that? Because their files are like really large files. So and I initially I told you, right, they wanted to make full use of the bandwidth. So they decided that we'll keep 64 MB of chunk size. So whenever a user calls it, it gets this entire 64 MB chunk. And this reduces, one importance is that it reduces interaction with master again and again with different byte offset. And it will now have like the most of the byte offset will be over here in this particular chunk, if this is what user wants, right? So um, and for random reads, what happens is, for example, there are random reads in the chunk. What this is the responsibility of application, that what it tries to do is it tries to align those small random reads together, and they sort it so that now it knows like how many chunks it would want, and whether all of these are from the same chunk, and then they could get all of these together in one go rather than, performing multiple random reads. So these are the reasons. And another thing is these.
Sorry, I have a question. So, does the GFS client allows for the application to read multiple chunks in parallel?
Yes.
Basically to download faster.
Yeah. It allows parallel. You can consider read, write, append, everything is parallel in GFS.
Okay, thanks.
The other thing is, so hotspots, right? We were talking about. So first, let's come to how replication would look like in a particular chunk. How a replication would look like for a particular chunk. For example, this is chunk 1, 2, and 3, and so the replication would not be like something like 1, 2, 3 and 1, 2, 3, right? Because there is a possibility that all these read write heavy operations are for 1, 2, 3. So it would look something like, these are my 3 chunk servers. So this is 1, this is 1, and this is 1, and this is 4, 2, 7, something like that. So it will distribute it across in such a way that to reduce the hotspots. But there was one scenario that they mentioned that executable was written as a single chunk. So this exe file was over here, and now whenever the client, a lot of clients started trying to access this executable, and it became a hotspot. And so what workaround? So they did a workaround for this. So they decided that exe should have a higher replication factor and not just 3. And the other long-term solution that they thought about is that clients should read data from other clients. Like if a heavy operation is going on here, then for 7, you should be reading it from some other replication of 7 and not from here. So this is the long-term solution that they came up with.
So does this mean that there are multiple active replicas one can read from?
Yes. There are always n active replicas, and this n is configured by you, like basically the application.
I see. And for each file, this can be configured.
Yeah.
Got it.
File,
Okay. And
each chunk, sorry.
okay. And it is the master's responsibility to give the right replication ID or the chunk server, because one file or one particular chunk can be present from multiple replicas. So master would decide and do some load balancing. And the
Yes,
GFS
exactly.
client stop. Okay.
Yeah, it's master's responsibility. Yeah. So
I have a question here.
mhm.
So if somebody want to write and there are multiple replicas in a chunk, so every application that is trying to write, there could be a number of application also, right?
Yes.
Or there is only one application.
No. There will be multiple replication. There will be multiple replication, right? Yeah. So it will write together, and we'll come to it when I'll go through this algorithm of read, write, append, record.
Okay. So
Yeah.
that sounds fine.
So I'm going to come to that in I think another 5 minutes. I think I should be there.
Thank you.
Yeah, no problem. So yeah, then we were talking about this metadata, right? So did any of you thought like this metadata, right? This master is keeping it in memory. So if it's keeping it in memory and it is keeping this metadata for each chunk, will that be a problem? So it's not a problem because, for 64 MB of chunk, for example, even if I have 100 servers, right? And I have around maybe 16,000 chunks in each of the servers. And then the data, the size of metadata that I'm going to keep is still 64 bytes. Then it's not a big deal, right? So it will be something about some MBs and not more. So it's not a problem. The other thing is what master keeps it as persistent or information, and what is not a persistent information. So here the location, except location, everything is persisted, because location is something that is not relevant to keep. And why it is that any chunk server can go down at any time. So if I keep this information, right, persisted at master, it's no use because it is subject to change, and it is subject to change a lot in the real time scenarios. So that's why it will be not persisted. Apart from that, every information here is persisted, that you can see the operation logs, the chunk ID, the ACL information, the versions, everything is persisted. So how,
Question.
yeah.
Since there are multiple replicas, does the master keep information of all the replicas?
Yes.
And it gives a, and then when somebody is asking to that I want to perform a read, now it will give the same replica, or it could it will do a round robin kind of thing. If somebody else is asking for the same, it will give a different one.
It will just give any one. There is no round robin.
Okay. Now, when somebody is asking, when a client is asking that I want to read a chunk, or when the client asks, does it also ask that I want to read or write, or anything is okay?
No, anything. It can ask for any. No, actually, the API call is read, right? So you will, the client will send read API to the master.
And if client want to write, then
Then it will call
then
with write API. Yeah, I think I
no.
have these. Yeah, it will look something like that. Although it's not from the paper, but like what I understood, it will look something like this.
So this API is a communication between client and chunk, or between client and master.
So this is GFS client API. You can ignore the last one, which is not basically the GFS client API. This chunk state, we should cut this out. So these
Yeah,
three
but
are.
where,
Mhm.
yeah,
Oh,
but
this
where is that
is.
API? The communication between client and master.
Okay, I think let's go to that. So it is client and master, right? This is client and master.
Oh, so read and write are happening with the client and master, or they happen between client and chunk?
Client and chunk server. It happens between client and chunk server. So what happens is client needs to tell master that what I want to do, because it does not have chunk server information. Then master gets that information and provides with the chunk server ID. So
But there are
maybe
two
I can,
APIs, right?
yeah, there are multiple calls happening. The API will be different for both read and write and append record. So
So
something like
yeah, that
this
API
will,
looks like between client and application.
what, this one? No,
Yeah,
it's not
yeah,
between client
okay.
and application.
Because if it were between the client and the chunk server or the master, okay, this is between the client and the master.
Yes.
Yeah.
And okay, probably I can explain it in steps. It will be much easier to understand. So for example, we are doing read, right? So
Mhm.
for so first thing what will happen is there will be our application, and there is this GFS client. Okay.
Mhm.
And what GF application will tell GFS client is, I want to read this file and this is my offset. Now what
Correct.
GFS client does is it uses this file, it calculates an index and calls this read on master first. Okay, so this was first call, this is second call. Now master, what it will see is what file it needs to read and what is the index of chunk. So what it will do is master will find out the chunk handle ID, chunk handle, which is basically chunk ID, and the location, and replies it to GFS client. Now this operation is over. Now what will GFS client is do? It will cache this information here. Okay. And now whatever it wants to communicate it with, right? For example, these are our chunk server. Here is my chunk with the ID. For example, the chunk handle that master returned was A, and this is my A chunk handle. Now GFS client will send this request of read, file, and offset.
Okay, it's the same API. Are you saying? You're saying like same API goes to
Yeah,
master and
parameters
then
are
same.
different. Like with master, it is sending index. With
Okay.
chunk server, it is sending offset because it wants to
Yeah.
read from certain offset, right?
Yeah. Correct.
Yeah, and then this call will be data. Basically, the data bytes will be returned to GFS client, and then this data will be returned to application.
Yeah. So my question was like, yeah, so there is a difference between, I'm not sure, like, if you want to jump into later on, that's fine. It was more or less about, since there are n number of copies, to reduce the load, there are a lot of people reading the same file or so, or same chunk. It might make one client or one chunk server a hotspot. So if multiple people are reading from the same file or same chunk, will master give a different one to the next caller, or it will always give one to the reader as the same chunk server?
So
One chunk is being read by multiple, at the same time or so, same client, same applications, different application and different client. So will master give a different path, chunk server, or it will give the same path?
So what master gives is there are two things basically. One thing is that what master can do is it can return the same one, right? Like whatever this index, right? The specified to which are the locations of the chunks. It can return that any one location. Now, in terms of if there is a hotspot, it's master's responsibility how to rebalance. So there will be a process going on in the master. So I think master should take care of this information as well. Although it is not deliberately told in the paper, but master should take care of if there are so many. If something is a hotspot, then it should probably provide a secondary rather than a primary.
So does the application have control over, because application is aware, right? Like what kind of access patterns, like how much read load expected. So does the application have control over how many replicas can be created?
Yes.
Okay.
Application has control over replication factor. So I told, right, the n value is configurable by you, application.
But that replication factor is for the from the fault tolerance. There are two replications, right? One is for the fault tolerance to make sure you have at least one replica, you don't lose completely from the availability perspective.
Yes.
Second thing is re-replication. So you want to be the re-replications can be in the same rack, same data center, because you want to provide more replicas so that if there is a hotspot, if there is like a lot of traffic, then the traffic, the reads can be routed to different replicas to reduce hotspots, right? So does the application have control over the read replication factor also?
So yeah, good question actually. So what I understood from here is the read for read, right? So when write happens, right, it happens on all the replicas. So read replication, there is no factor as such, but whenever master is called, I think master should be able to, because master tells you where you have to get that information. So you can always the master can always tell to go to a different location rather than that. And for I think here replication is more related to load balancing and not fault tolerance. Reason I say this because whenever they do a write, they always make sure that all replicas are written together, and even if one fails, there will be a failure returned to the client. So that's why I think it is not more fault tolerant related replication here, but more of load balancing related replication. I don't know how true it is, but this is what I think.
Right, the algorithm is generally slightly different. If it's for the fault tolerance, they replicate among different availability zones data centers. and for load balancing, right? For that they can replicate within the same data center, same rack.
Yeah, I agree with you. Like whatever I've read, replication is mostly related to, not mostly, every time related to fault tolerance and not load balancing.
Okay,
Yeah.
okay, that makes sense.
So we also touched base on one thing earlier. Somebody said like, that it's a HDFS make sure that the compute is running on the same rack as that of a storage or replica, correct? So now if we have three different replicas and the compute is, we have different compute on all these replicas. So whose responsibility it is? Because there are three copies, right? And if master will give any one of them, but the compute is going to run on which one of them, how that is handled, that it get that particular copy which is close to it.
So, this part is entirely handled by a separate component. Like HDFS doesn't worry, sorry, the GFS or HDFS, they don't worry about this. Like in Hadoop, they have separate component called job resource manager or something that takes care of all that. Based on what the master gives, okay, these three replicas are on this on these, and then we have these many slots available on these many machines, then let's choose the closest one. So this, it's a
So,
separate component that handles, I think.
okay, so in this read call that GFS client made, will it get all three or it will get only one?
I think the when it first calls the master, I don't know, the presenter can explain it in better, but I think it gives all the three chunks, and the resource manager decides which to use based on which compute slots are available.
Okay. So I think there are two things, but that's what I read in with respect to, right, that the master returns like all the primary, secondary information. But I don't know how it happens in HDFS, but in here in GFS, they were returning was just one chunk handle ID. So I don't think so that you have the leverage here then to decide like which one is closest based on the hops.
Okay, got it. Thanks.
Yeah.
But is the GFS client telling its own information to master also where it is, or it is no?
No,
If
it doesn't need it to, right? Because GFS client is calling master, so it doesn't matter where GFS client lies.
yeah, the reason I thought is like, okay, that's fine. We can move on.
No, we can discuss it. I think everything should be clear. And it is
Yeah.
better for me. It becomes much more clear when I make people understand something.
Yeah, my question was primarily on this is a kind of a basic thing in a big data system that it has to be the closest copy. That makes it more efficient, and it also makes sure that if there are n number of applications running, if they get the closest copy, then everybody will be able to benefit from that. Now, I was just trying to understand, since we know that there will be multiple copies in a different zone or different rack, to for fault tolerant and actually optimization or efficiency as well. So I was just thinking like how or which component or how it is decided that I will get that copy that is closest to me.
Okay. For example, if you're returned with all the copies, right? Right now, it's your responsibility to identify which one is my closest one, and that happens here. In the case of write, that happens because write, you have to transfer data. So, and it has to happen all the replicas. So first it happens on the nearest one. And what I can think of a logic and how it would have been implemented is there is something called as network hops. When you basically, if you nmap on any DNS website, right, you can see how many hops it has taken in order to reach that website. So if you can count like which one has like minimum hops, I think that's your winner. This is the solution I could think of. Like,
and in Hadoop ecosystem, how do you know which one is the closest? So we maintain a separate for replication and fault tolerance. We have separate file called topology file. We tell that okay, these many files are here and all that. I think based on that also you can decide whether this chunk is in my rack or it's in out of the rack and something like that.
Yeah, I think I understand that question, but what I'm just trying to understand here is if there is a single API call that goes from GFS client to master, that I want to read a chunk, and there are three different chunks available, and at a different location. How it is determined that if master will give me only one, then master doesn't know where I am because I'm not providing that information, right? And that could be a far off location, right? How we are determining that is that captured here, that how this is determined that I should get the closest copy in this design.
Uh, sorry, I want to say something. Actually, master doesn't know where it's coming from because it's a file system. So there is a
Yeah.
separate component, entirely separate component, which has a job of negotiating and providing resources. That resource component knows. So let's say if I'm submitting a bad job, a map reduce job, right? We also even don't know where to submit the job. Generally, if we are thinking like, okay, we are reading a file on someone's computer, that's a rare scenario. But it is what it is made up for, like somebody's running, it's a bad job. So I will create a bad job. Okay, let's do a word count and submit the job to that separate component resource negotiator. That resource negotiator knows where are all the jobs are running. Then it finds, okay, where is the slot available? And then it starts running the job from that slot. And from there, now you know which machine you are in, which rack you are in, like where are you right now inside the cluster. And from there, it makes different calls to like master, okay, give me the copies and all. And that's how you know where you are and which chunks you need to read. But it's all handled by these components. The user never worries about all these.
Okay.
Yeah,
Makes sense.
another thing to add to that, I remember like there is a section in the research paper about, fault tolerance and data integrity, I think probably there or somewhere, where I read like they don't, like in GFS, they don't implement a tree-like structure that you suggested, right, in HDFS, and they rely on IP address. I will have to see which section I read it on, but like, yeah, somewhere I think there where, I don't remember exactly. I'm checking the paper right now, but I don't remember where I read it.
So
Probably in data flow or somewhere. Yeah, I think, yeah.
looking at the diagram which they have for the file system, I think they have not talked much about how they're handling this availability zones and getting the nearest replica. And probably they have not discussed about that much. Probably they have abstracted out that piece, that it could be an improvement on top of Google file system, but probably they have not talked about it. Looking at the diagram,
Possibly.
Yeah, actually, yeah, this information, yeah, in data flow, right? No, yeah, I found out where I read it. So, so to fully utilize each machine's network bandwidth, the data is pushed linearly along a chain of chunk servers rather than distributed in some other topology, example tree or something. So that's what they said. So that and here only somewhere they mentioned that they rely more on IP address in order to find out where is the closest replica, closest piece of chunk where they want to read the data from.
Yeah, that
Yeah,
closest
you
piece of
can
chunk
go through
actually.
section 3, system interaction. I think 3.1 and 3.2 has this information.
Oh, so okay, then is it possible? Oh, right. So then, okay, I see one approach could be that, so every client has their own cache, right? So based on the IP address of the client request to the master, and it also has this information that where the replicas are. So probably it will return the replica which is closest to the IP address of client, right? And so
The question, how? Master doesn't know this information, right?
the IP address of the client.
Yeah, that's
Okay.
That's the caveat, right? We were thinking like it doesn't know where the client is, and it doesn't need to know actually.
So then what is the use of IP address?
Yeah, not IP address of client. So I'm not talking about read, but in write, what you get is all the. Am my voice is echoing? Is it?
Yeah, a little bit.
Okay. So what happens is in write operations, that because that's what I read, it gives you information of all the replicas because you're going to do write on all the replicas simultaneously. Like parallelly. So what happens is there you will first transfer your data to the nearest replica, and that information is taken through IP address,
But
like how which one is closest.
isn't the why would it do that? Because there's no, when you are writing, you should be writing to all the three replicas, right? It's not
Yes.
like, and since it's an append only, what does it do? Like, does it write to only one replica, and then internal sync job that you mentioned will take care of syncing with the other
No.
replicas, or how?
Yeah, so let's go through replica, this write operation, right? So first operation will be similar. Application will call to GFS client and GFS will call master, right? Now GFS will call master with, write request, and the probably it will have a data and index, right? Now master will give me the information of all the chunks.
Question.
Yeah.
Sorry, I think maybe we are missing. When GFS client is calling master, what it is expecting is only in chunk server detail, right?
Yeah.
If this write API will have data in it, then this incurs a network latency. This need not be passed on to master. Master has nothing to do with the data, right?
Yeah, makes sense. Yeah, makes sense. Yeah, you can remove it. This API calls, this is not given in the paper anywhere. This is what I wrote, and that's what my interpretation is. So everyone can have a different interpretation of the algorithm. Yeah. So it makes sense. Yeah, you can just return the this chunk locations basically, chunk IDs of like it will be a array. There will be a primary, and there will be secondary replicas, right? So now once master has written this information, what GFS is going to do is it will pass this data into all these replica. For this is my primary and this is my secondary. Okay, and there will be this buffer where all this data will be written. Now what my primary does is it decides the order, like this will be the what will be the order of these writes, because we know that there could be concurrent writes. Okay, another difference is write also sends offset, like where it wants to write, because it could be a overwriting operation, right? So now my primary decides the operation and it tells the secondary what order it has to apply these operation in, and then the secondary applies these operation along with primary. And this is how write is done. And this is, you were talking about, someone was asking about synchronization. So synchronization is not taken care by master. It's the responsibility of the primary chunk to take care of synchronization.
A question. So this one chunk server is primary. Who tells this that this is primary? Is it master?
Master.
Or so master will give an information that one has to be treated as a primary.
Yeah. So there is another concept. Now it's like going too much forward and backward, but it's okay. Like let's go with the flow. So what happens is there is something called as lease, right? And what happens is master. So initially there is no primary, right? So initially, like if I call C primary, it will be empty. Now master knows that there is no primary. I have to make someone primary. So I showed right in the slide over here that everything has a version, like every chunk has a version. So based on this version, master will decide who will be my primary. So for example, it made chunk 2 as primary, and it will give a lease of 60 seconds for this primary. Now what happens is, in these heartbeat that gets transferred between the chunk server and master, it renews the lease, right? And if in case the primary fails, the master is supposed to make someone a new primary, right? So that's how this whole thing takes place. So with lease, there are two options, that there is happening of renewing lease, and another one is no lease were renewed and it failed. So now there is a timeout of that 60 seconds, and master chooses a new primary, right? Now some of you might have a question that what happens if there is a network partition, right? Now you can have two brains in the system. So for example, if I had this chunk 1 and it was primary, and I had chunk 2 which is secondary, and chunk 3 which is secondary, right? Now there was a network partition and master couldn't reach this chunk 1, but it is able to reach C2 and C3. So it will decide the lease between C2 and C3 whom I have to give it to. But the thing over here, which is different than Raft, I would say, is that like master will only provide lease when there is the complete timeout. So that 60-second information, right, it is there at master level also. So once this 60 seconds is completed, then only a new primary will be assigned, to avoid this two brains problem in a system. So this is the concept of lease.
So it means that if primary was down, nobody will be able to write for next 60 seconds, correct?
If primary is down, yeah, for some time nobody will be able to write. Yeah, unless this timeout happens, that is where the timeout is so less.
So even if the earlier primary was up, but nobody was able to communicate with it, maybe some network issue or so.
Yeah.
It will know, the old primary will know now my 60 seconds have expired. I should discard whatever I get.
Not discard. This primary will no more be primary because its lease did not get renewed, so it becomes a secondary.
Then when it becomes from primary to secondary, it has to refresh its content or chunks.
Yeah, so what happens in some scenario is for example, if it came up early, then it will just synchronize. If not, that what happens is, as soon as, because GFS give you a guarantee, and that guarantee is every time whatever number of replication factor that you have selected, right, that n value will always be true. So as soon as the master sees that, okay, my one of the replication is down, it will generate another replication for you. So basically after this, what happens is, since it's it's not updated, this is more like a garbage collection now for master.
Got it. Thanks. Maybe so master will spin up a new replica.
Yeah, it will spin up as soon as it sees, okay, my replication factor property is not meeting, it will spin up a new replica. It will ask primary to help this replica to have the chunks that are there in this, have this chunk over here, basically, with all the proper file data, whatever it is there, that was there in this chunk. And then it, like, this becomes like now unimportant, and this becomes our inactive or garbage collection chunk, which will be removed after certain time.
Got it. Thanks.
So Shreya, is GFS, can we update a file inside a GFS?
Update a file, you mean? Yeah, updating a file it's a file system, right? You can update a file in any file system.
No, in HDFS we cannot.
Oh, is it? No, here you can. They provide all these operations: create, read, update, delete, open, close.
I mean, let's say if we want to update in HDFS, you do not go and do an in-place update. Instead of, it writes the whole new file with the update.
Actually, Yeah, there are two types of data mutation here. One is write, another one is record append. So what happens in write? It writes to a byte offset. So byte offset will be somewhere, right, in the chunk. Oh, for example, if this is my byte offset, so it will go and overwrite this particular data. And record append is what I think happens in HDFS, where it will just go and append the record in the end.
So the byte offset update, it has to be of the same size or it can be of different size.
Different size as.
So if it contain, let's say, a sequence of characters like A B C D. So can you if there are 4 characters A B C D, you can replace them by XYZ, or it has to be of same length?
No, it doesn't matter, right? If I gave this byte offset and whatever my data is, it will be updated up till here only. So it doesn't matter what was there before, because you have chosen it to override it.
I think
So you can cut short. Go ahead.
Yeah, I think I disagree with that, because that's what the byte offset is, right? How many bytes you are away from the origin. So as Hitesh has said, it has to have the same length, isn't it? Because that's what the byte offset means.
Correct.
Inside a file, like how far away you are from the 0th byte.
Yeah, so that's the place from where you have to start writing, right?
No, I'm saying, let's say if we have a one file, whatever you're showing here, right? So the first line would have a byte as 0. Then let's say there are 128 bytes after that. Then the next line will have 129th. So if you are saying, let's say, change any record between these, the byte offset will change them.
Change record. Yeah, so it should start writing from here, no?
No, it's fine. It can write it there. But what was the question of Hitesh was the data has to have the same length, because that's what the byte offset means. How many bytes you're away from the source.
But
It's
the
not
data
like it's not an index, or it's not a random number. It is dependent on the data. That's what I'm trying to say.
Yeah, I probably am not able to understand something. So for example, I have to write ABC, right? And this is the data. I can
So
go and
for
write
this,
it on the place where I have to write. So whatever was under this, it doesn't matter.
So the question is, so let's say at that byte offset, if the data is EFGH, right? There are 4 characters, and now you're replacing with ABC. So will we have G left because 3 characters you have replaced?
Yeah, it will be. It will be
Yeah.
obviously. Yeah.
So no, but yeah, I mean, obviously the user might not have expected that. He might have wanted that everything after this offset is replaced by ABC. So that, yeah, or he might have wanted that only these many. I don't know, but yeah. So that,
so
I think that, yeah.
what I was thinking, Shreya, is, correct me if I'm wrong. I never thought of this question. Let's say we have a file with the 2 lines, ABC on line 1 and DEF on line 2.
Okay.
So the byte offset for the line 1 will be 0, and the byte offset for the line 2 will be 4.
Okay. Yeah.
So, I mean, that's what I was thinking. That's how the byte offset will work. And if the file is arranged in such a way, then let's say if I want to change ABC to, let's say, something just XY, then the byte offset will not matter, because what you're gonna put into those empty space.
Okay.
Yeah.
I
So
was seeing it more as overwriting the data there.
so Shreya, the thing here is you have 1 TB file, right, which we are dividing into 64 MB chunks. Correct. Now, if you remove something in between, or or you add something in between, you have to shift everything that is at the end of it, right? Yeah, when you write into a simple file, right, you type in between, so your byte offset changes for the rest of the file. That will invalidate, or that will change all the content afterward, right?
Yeah, I was not thinking it as an insertion operation rather than a override operation.
An overwrite operation means it has to be of the same size, right? when you say overwrite, you're overwriting some bytes. It has to be of the same size. If that size is smaller, then you are shrinking. If you add it bigger, you are expanding. Correct?
Uh-huh.
Both the operations where you whether you shrink or you add additionally, it is going to change everything that is afterward. It's a sequence of bytes, right, within a file. So if your write operation will either if it is not of the same size, it can only be two options, right? Shrink or expand. In both the scenarios, your all the chunks afterward, they will change.
Okay. I
So
probably, might have to go and read it again. But I'm
yeah,
not pretty sure about, like, my understanding of it was a little different.
yeah.
So
And
In
probably I should
general,
just go back, and reread it.
I think it's a maybe I think you'll be able to find it. It's a regular thing actually in any file system operations when you're writing on the byte offset or so.
Yeah, but you are right, but it's just thing that like I was not thinking if it of as a, shifting the bytes, because it's not, and I didn't think of it in that way because I didn't see that in the paper.
Yeah, there are things that are hidden also. I think it's a very interesting thing if it allows sync and expand in between. That's and how it is handled. It can increase the size from 64 MB also, or it has a potential to add a smaller chunk in between. How that will be handled. So that's a
Yeah, the size is fixed. It cannot be increased. So if it goes beyond the size, you probably need a new chunk. That I'm
yeah,
pretty sure about. So
correct. So
mhm.
you are saying if you will try to write a bigger size in an
Mhm.
offset, then it will increase the chunk. It will introduce a new chunk in between.
It will introduce a new chunk, somewhere in the
Yeah,
chunks.
if you introduce a new chunk, then your master has to be updated and it has to shift all the chunks afterward by one more, right? So it add a significant
Actually,
complexity if such an
that's the
operation is
beauty
allowed.
of it. It doesn't have to introduce any like like any chunk like that, because so
If
you're
it
saying
doesn't have
because the
to,
write is in the middle. Okay, got it. Yeah.
yeah,
So,
correct.
but master still will need to have only like information of chunk location. This index thing is calculated by GFS client because it
No, no,
knows,
no,
right,
no.
which offset. Yeah.
Index thing is like when you request a master, master has a sequence of, things which file is this index belonging to, right?
Yeah. So it,
If you
so, but
insert in between, you're moving it. If you insert between, if you insert a bigger one in between, it will add another chunk because you said right, it cannot be beyond 64 MB.
Yeah, I get it.
Right.
But I was thinking this is more like chunk ID, right? So even like if I add a new chunk, that will have a new ID.
So
Only like
let's say your chunk number two. Your chunk number two here is of 64 MB, correct?
mhm.
If you allow a write operation on chunk number two with a bigger size, then you are introducing a chunk between two and three,
Yes, exactly.
right? So your number three has to become number four, and there will be one smaller size chunk between two and three.
Yeah, that's what I'm thinking. That you don't need to update. Like you don't have to update the chunk ID. Now chunk ID is because uniquely identified. You can add a chunk 4, and you can have some chunk server where the information is kept. What you have to arrange is index, and that is like more not related to master.
Mm.
Index is
So you,
calculated by GFS client.
correct. So you are saying chunk ID is not a sequential number.
Yeah, it need not be, right? It's a 64-bit. It could be anything.
Okay. Now
Yeah.
so when a client will request that give me a chunk ID for a given offset, how it will it how master will determine? What
Because
is the
chunk
logic
is
behind
giving you
determining?
ID already, right? So it provides you the index of like where your file will belong. That calculation happens on the client side. Basically, you will have the whole, that the size file is of size, chunk is of size 64 MB, and then
Mhm.
you have your offset. Then you divide your offset, right? And then you
And
know which
then
index you have to go, which index that you're trying to call.
okay, let's take an
So I think
example what you
probably
just said.
another mapping that we need over here is index should be there, which tells you which chunk ID, which index.
Correct.
Yeah. So yeah, there should be one more column here for index.
Yeah, that adds a good complexity to this piece. If increase or reduce, or if somebody get rid of one index in between, or the one chunk in between, so that add a significant complexity to this. But if that support is provided here, that's amazing to see.
Yeah, I think that should be definitely supported here because it's a file system. I don't think so. There is just only.
Although, yeah, I don't know, but I think somewhere they also mentioned that their more focus is on append only.
Yeah, they said like random writes and random reads are so low that they don't care about it. That's what they mentioned. But yeah,
Okay. They are
don't
also like
provide.
STFS, probably, that
Yeah.
they are good at append only. And
Yeah, even they have this append. Append is a different operation. So let's see what append looks like. So if anyone has any question more on writes, we can go through it, or we can move to append.
Yeah, I think we can move to append, unless anybody else.
So in append, the difference is the information will be passed on in similar way. Like application will tell GFS will go to master, ask for the information of chunk. That remains same. Now extra operation that's going to happen is when GFS will send data to primary will first validate, because it's an append operation, right? And we have 64 MB fixed size of a chunk. So when data is provided to primary, it sees whether that particular data can come in the chunk. If it cannot, then what happens is it adds padding in its chunk, stating that it is like filled, and tells its secondaries also to fill it with the padding, and returns to the client that I cannot serve you this request because I'm already full. Then GFS, what it does, it again goes to the master, and because there is padding here now, master knows that there is no more space for this request to complete. It creates a new chunk now in any chunk server, and then it asks the GFS and provides the GFS with that new chunk information. Now what GFS does is it provides data to that particular chunk, which will be a different primary now, and it's secondary. And the other operations are similar, like first it would go to buffer, and then primary decides the order, and then it is returned to the chunk. So that's the difference between write and append. Apart from this, yeah, there are some issues that can happen. For example, if everything is successful, we don't have a problem. But what happens if one of the secondary fails while appending? So as I told before, these operations are all synchronous. If one of the operation fails, secondary will return probably a false, that I couldn't write the data. And then what primary does is it also returns a false, that this operation is a failure, you have to retry. So what GFS does is it retries this operation. So now the thing is that if it goes to primary again, right? And since it's an append operation, there is a possibility there could be, duplication on the primary side. If because the operation will be done again. So for this, the Google says that you can have like something called as record identifiers, which can duplicate all these records But this all happens on the application level. So this all things are taken care by application. So deduplicating any records or something like that. And if the application is okay with it, then it's fine. But there are like, this is one of the drawbacks, or like it is expected by Google that, you know, some duplicates is expected. So this can happen when, if someone reads the record, there can be a duplicate there.
Yeah,
So,
question.
yeah.
So when you are writing, so the write call from GFS client goes to all three, correct?
Yeah.
Then what is primary doing with secondary? I think you said it. Probably maybe I didn't understand. What
Oh yeah.
primary ensures?
Yeah. I told right that it decides the order, because it could be a concurrent operation, right? And we want them to be in sync, like in same order. Whatever writes are performed, they should be performed together. So primary decides the order, and it tells secondary, like, you know, this is the order and you should also apply it in the same order that I applied to.
It tells secondary or it tells GFS client? If the request is coming from GFS, so if the request is coming from GFS client directly to secondaries, they will not perform the operation?
They will put the data in buffer.
Okay, they will put the data in buffer.
Yeah,
And then
these
primary.
are buffer.
Okay. Okay, so the request from GFS client to all the three copies is to put something in buffer only for primary, secondary, all of them.
Yes.
And then primary will ask secondaries apply. So secondary 1 has already applied, secondary 2 failed.
Mm-hmm.
Right? So secondary 1 has a stale replica, but primary returned failed to GFS client. How will secondary 1 replica recover?
Secondary 1 replica will not recover. The operation is already done.
Operation has already failed, right?
No, on secondary 1, the operation already was successful, right?
Correct. So secondary 1 operation is successful, so write is done. But we returned fail to GFS client because secondary 2 did not pass.
Yes.
How will secondary 1 reverse back to its original state?
Yeah, it doesn't. It doesn't. That's what it is about. Like, you know, you can see duplicates. So on application level, you can provide, you know, certain things, like, you know, you can have this record identifiers which can allow you to dedupe.
So the question comes, like secondary 1 has something extra than secondary 2 or primary. Now there is also a master file living somewhere else, right? So how will this chunk from S1, it will go to primary, will go to the main file or not?
I didn't understand your question. Are you asking that this S1 is in buffer and now while writing?
See, the chunks are stored in chunk servers, but the actual file is somewhere else, right? The 1 TB file, correct? Or bigger files, they are somewhere else, right?
Can you repeat?
In GFS, the files are bigger in size and the chunks are stored on chunk server, correct?
Mm-hmm.
Then this chunk has to be made to, you know, this chunk, the changes in these chunk have to be applied to a master file.
Master file.
So, okay.
I still didn't get, like, you know,
I think
these chunks are the data, right? The file data.
So the chunks are the blocks of that file, right?
Yeah.
Yeah. There is no actual bigger file?
No, I don't think so, because all the chunks represent that file.
Okay. I think I was probably missing this piece. My bad.
Yeah,
Thank
so
you.
like you can understand it in such way. This is one file and it is of 100 TB. Now what you can do is this file will be divided into 64 MB of chunks, and it can be placed in some chunk servers. So you can understand it in such way.
Yeah. Okay, there is no actual 100 TB file residing somewhere else whose chunks are represented here on chunk server, correct?
Mm-hmm. Yeah. So initially I said, right, inexpensive hardwares, right? This is the concept, you know, you want to not have like really, and keeping your file distributed in the system using cheap hardware. Yeah.
Thanks. So, you know, your S1 has additional data, or your S2 and P does not have. If somebody is reading,
no,
so it is.
My P also has additional data. Primary
Primary has applied already?
Yes, primary applies and it tells like S1 and S2 also, this is the order, please apply.
Okay, now the question comes is like, since some of the replicas does not have data and some of the replicas has data, now probably GFS client, when it failed, it will not try to rewrite again. Let's say.
And why is that?
Okay.
Why it will not rewrite?
Let's say there was a customer transaction also, right?
Oh, so
GFS
there is
tried
no
in
transaction concept here.
No. So help me understand. A request to write. So let's these are log files. Think like something log file or some information also. Now GFS
Yeah,
is
log
trying
file.
to write some. Let's see some data GFS want to write, and then it is not. It is trying. It was not able to because of S2 was down or some issue, right? Now that data has made it to some file PNS1. It has not made it to S2.
Yes.
Right? So some readers will get that content, some reader will not.
No, that won't happen, right?
You are going with an assumption that if a failure has happened via GFS client, it will try till it succeed.
Yeah,
So,
it will retry.
So
Okay,
another
and
thing
now
is,
even if we, okay, sorry, yeah, go ahead.
another thing is, so if it's not retried, and let's say if P and S has that data, so now I think Hitesh's question is, so that data was not supposed to be there because client has not retried, but it is there, right? And I think that's the difference. So these kind of just Google file system you will not use for a system where you want that strongly consistent data for like banking or something where you have information which is not supposed to be there. We are assuming we are building such kind of system which are those append only logs where it is okay to have these kind of inconsistencies in the data, that it is there although it is not supposed to be there. And
that makes sense.
This is true for like a lot of systems like logging and analytics kind of system where it's okay if you have that extra piece of information.
Yeah. So another question comes to my mind is with this P and S1 and S2. It's like, let's say we are appending to the file and now 64 MB has reached. A new chunk need to be introduced, right? So your P and S1 will reach 64 MB early. Your S2 will not reach because some of the writes were not successful on S2. So there will be, so some of the chunks will be smaller than 64 MB and some will be bigger.
Yeah, to add to that point, we maintain versions, right? So that the concept of version is like if something is behind the version, master will know it because master and chunk servers talks to each other like if in every moment, like in some time that what is the status. And so once it knows that okay, it's version behind and this needs a fix, what master does is either it re-replicates the chunk and invalidates this chunk.
Okay. And then
So
maybe
this is a way, to make it consistent.
Yeah, okay. I got it. Cool. Thank you.
Yeah. So after this, I think we all were talking about, how this data is being passed in like near location and far location, how the client pushes the data to all replicas. So in write, what happens is this buffer thing that in buffer you push the data, that happens in this sequence. The sequence is, so if GFS client lies here, so whichever is nearest, the data will be pushed to it first. Like for example, in here I just mark these 3 arrows that data will go to primary, secondary 1, secondary 2, but it happens in an order, and that order is, for example, even if this was secondary, this is primary, and this was another secondary. So in the buffer, right, the data will first go to the nearest secondary, then this will be passed to primary and then to the secondary. And then once the data is written to the buffer, then primary decides what the order is and then gives that information to secondary, and then primary can return true or false based on the operation that happened. So this is one like important thing.
So how does primary know it is primary? It talks to master as well?
Yeah, it has that heartbeat, right? It is given that lease that we talked about over here. somewhere.
And
I
then it
can-
also knows what the secondaries are. Okay.
Yeah, definitely, yeah.
Okay. Thanks.
So there are some metadata kept at chunk level as well, like, who are its peers, basically. And that information is not kept persisted because, like, that is subject to change. The peers are subject to change. And also, like, what is the timeout that is being going on right now, because the lease is of 60 seconds, it has to renew the lease. So it has to keep that information as well. Apart from that, I think we talked briefly upon what will happen if, like, I think we can consider like each scenarios now here. We did already these algorithms, and this was like the APIs, and now some scenarios to consider are if master is down and if chunk server are down. So let's see what happens in these scenarios. So if master is down, there is something called as operation logs that we keep. These operation logs are basically like what all happened on the master level. So for example, a new chunk got created, or a snapshot was taken, or any information that has been going on in master, that all will be kept in these operation logs. And then whenever the master is down and whenever it comes up, it can, and these operation logs are written in a remote location and on some of the shadow masters, right? And whenever the master comes up, it can again retrieve the information from this remote location and reinstate its state. So that's what master does. And if in case the master doesn't comes up in the expected time or the timeout, then a shadow master takes its place and reads from this remote logs, because the shadow master and also, like, this is one of the important operation, that whatever happens at master, it appends to the remote location, and once that is done, then only it returns success to the client. So that that it makes sure that there is always a copy which it can get information from. So if a shadow master has to become a master, it compares all its state with remote, and if something is not applied, it applies it. Another question that I think can come to people's mind is this operation logs, right? Over time, it can become really huge. So for that, there is a concept of checkpoints. You have these checkpoints in the logs, and the older checkpoints you can delete, and with the checkpoints, the master can reinstate its state. So the operation logs doesn't gets bigger. So this is what happens if a master is down. Now, when a client is down, the chunk server is down, what happens is there are multiple scenarios. So for example, this is my chunk server, C1, C2, C3, and then there was some chunk which went down with this particular chunk. Then what will happen is master will know, since this chunk is down, it will create this chunk in any of these other servers. So for example, there was some C4 as well. So this A will be created here, and it will make sure that every time that replication factor is property is maintained. And there is an order of doing this. Order in the sense, for example, there could be many machines that could be down, right? There could be multiple chunks that would be losing their replication property. So there is an order of whoever has, like, if, for example, for a chunk, if one of the replica is down, it will give precedence, the master will give precedence to the one which will have like two replicas down than one. So this is how it decides. Also, it if there is a replica which is down and there are so many client requests for that particular chunk, then it will first bring that replica up in order to distribute the load. So this is about how, like, chunk servers are reinstated. The other Yeah, and there is a possibility, right? It could have like multiple chunks. So like the scenario will be same of, bringing like, redistributing. It's not like it will create another server and make the copy of that. That is not the case. That will not happen. Whatever chunks are missing replicas, that is the operation that is going to happen. So some of the important operations of master are the lease. We already talked about this. The another one is replica placement, and that is where should you place the replica. And I think we talked briefly also upon this, that how between it should be kept in different racks, so that if one rack is down, the replicas are not affected. And the other one is how the replicas are created, and re-replication also we talked about. And rebalancing is like, if the read-write requests are too much on a particular chunk server, then you have to rebalance it in order to divide that load and redistribute the load by moving these replicas. So this is about rebalancing. The other one is garbage collection. So garbage collection happens in two cases. One is if a file is deleted, and if the chunk is no more the chunk that we want it to be, like, if it is way beyond, way beyond the particular version, or all the files inside that chunk are deleted, if they were smaller files, right? Then we would want this garbage collection to take place. So it's a lazy operation. It happens only when the master is idle. What happens here is for files are made hidden files. Like in any Linux system, it will be replaced with dot. And then what happens after that is for 3 days, master keeps a track, like, this file. So a timestamp is also logged. So master keeps a track that, okay, from past 3 days, this is a file which is deleted, and probably I should remove it from my namespace. So it removes it from there and deletes its metadata information. And same goes with chunk. In chunk, it sees that, if the chunk is not reachable from any file, then it removes the chunk information as well. Or if the chunk is behind the version, it removes the chunk, because now it doesn't matter like what that chunk was, because it already has a replica which is updated version. So that's about garbage collection. I think the other thing what happens, like why they made it like a lazy one, is because if somebody deleted it by mistake, then it should be easily recoverable. Like you can just rename the file, removing the dot, and it becomes a normal file. And also, like if you have deleted a file, you still want to access it, you can access with the renamed like one, the dot one. The other thing they said is, if you want to delete it, like, if the disk space is very compact, you cannot, have the deleted files lying there for 3 days, you can redelete the hidden file. So that will make sure that you have some space there. So these are some of the operations which happens in garbage collection. So I think there is something called a stale replica detection, which I have not written here, but the master maintains a chunk version number, right? To find out if a replica is up to date or not. And if it is not up to date, then we know, right? Master has this responsibility to remove the stale replica and put it in the garbage collection. So these are all things related, like together, how this is being done. The other thing about, and I think this will be probably the last section we'll be going through, is high availability and data integrity. So first, let's go through data integrity. So because high availability we mostly covered, chunk replication, master replication, other things. So in data integrity, what happens is, what if a chunk in a chunk server got corrupted? What will happen then? And how do you know that it is corrupted? So one thing that they said, right, you could have, chunks talking to each other, that okay, this is your state, this is my state, and then identify. But this will incur unnecessary network overhead. So what we can do is we can apply a checksum that happens in most file systems, and this checksum will be something like this, that if your chunk is of size 64 MB, it will be divided into the size of 64 KB each, and then you calculate the checksum of all these, right, and keep it. So whenever there is a read request, the checksum is calculated for that particular block, and then you can know that if it was corrupted or not. So if it is not corrupted, well and good, you can read it. There is also like a possibility that read could happen somewhere over here. So then it tries to read, it calculates the checksum of both of these blocks, and then checks whether it is good or not. And checksum has a very,
Question.
yeah.
So the read was whole chunk in one shot, right?
Yeah, this is like
Um,
64 MB chunk. I have divided it into 64 KB each for
but
checksum.
if the read is full 64 MB and the chunk is also 64 MB, then why to divide it?
No, it could be like, you want to read from a particular byte offset. You don't want to read this part.
Oh, so you are saying we have other options apart from reading full byte. My understanding was that the client is reading a full 64 MB in one shot,
Yeah,
then
yeah,
reading
you're right.
small portion of.
Yeah, it will take the whole 64 MB data, but clients actually give this information to the what do you call application, right? The information is passed so like if I asked I want to read only this much data, if you start giving me 64 MB of data, I might not like it, right? So I think GFS client will definitely get 64 MB of data, but from client to application, only the data that was required from the offset will go.
Okay, cool. Thank you.
Okay, so yeah, and that is why we need this checksum information. And I'm not sure though, but now if I think, could it be because like your file could be just 64 KB of file and it's a different file. Then if you want to calculate the checksum, I don't know if someone has something to say on top of it, like
Possibly, when your GFS, the chunk server, when it is providing some information to GFS client, maybe it's also along with the data, it is also providing a checksum details. Once it reaches the GFS client, it can match, calculate the checksum, and then compare with the checksum that is sent by the chunk server. And if it matches, it's good.
maybe, yeah, I don't know, like this information was not given, so I'm not sure like how it's implemented, but yeah, probably. But I don't know, like I can't say for sure what's happening inside this for checksum, but yeah, this is, and
there could
this,
be two type of there could be
yeah,
two
sorry,
type of corruption, right? There could be a corruption over the wire when it is sent from a chunk server to a client, or there could be corruption in the content on the chunk server itself. Now, if chunk server keep the metadata about all the chunks it has along with the checksum when it was written out there first, and it just persists that checksum, and then whenever the call comes along with the 64 MB data, it can also provide the checksum. So it serves both the purpose that since checksum was calculated before it was written, or actually right after it was written on chunk server, it should remain intact on the disk and also over the wire to the client.
yeah. But here, like in this data integrity, what they care about is corruption of the stored data. So what data is already stored in the machines. So they don't care about what is being written and if something got corrupted over the network. So like that's been mentioned in the paper. That's why I'm saying this. So
okay.
Yeah. So that's why I was thinking it's more about, checksumming while read in the chunk server, that it verifies the checksum of data blocks. And if there is a overlapping thing like happening over here, then it calculates the checksum of both of those bytes.
Then
Both
you're
of these blocks.
and then you're saying like the chunk server is calculating on the when it read when the request has come,
Mhm.
but it has to keep the checksum when it was created.
Yeah,
Right.
but it will read also, right? To compare.
Correct. So as soon as a new chunk server come into play, a new chunk comes to a chunk server, it calculates the checksum and persists it.
Yeah, it should persist. Yeah, it's a persisted information. Yes.
Okay.
Mhm.
Makes sense.
Yeah, and then they talk about like the read performance. So like it is not very like trivial. It's very trivial, I would say. It's not like, you anyways will be reading data. So while reading data, you could just calculate the checksum. So there is no extra IO operations there. Yeah, that's about checksum. I don't think so like anything is left. After that it is all about like what issues they found out in measurements. Although they didn't, it worked out pretty fine with mostly all of their applications for like reads and writes, and they tested on a cluster like which had one master and I think 16 chunk servers and 16 clients. So they tested for all the operations, and all their average read and writes were below the network bandwidth. So that's about their performance. So it worked out pretty well for them. Although like I was reading a blog about it, and then there was a conversation between two people and how like GFS actually worked out and people who implemented GFS client. So they said like there has to be a lot of workarounds because and a lot of things got better after even this paper, like when they were actually working on the system. So that's another thing. Yeah. So like not everything was, when they decided, not everything was perfect, but it like along the way it went better.
I was going to ask you this. This paper was published 10 years ago, right?
Mm-hmm.
And how is there's probably some improvements done on Google file system, or maybe some other distributed file system out there.
Mm-hmm.
Are you aware of new different designs or some of these improvements that possibly had happened?
I am not sure. I just read this as my first distributed file system, but if somebody else knows, they can talk about it. In this paper, I think they say that there are no caching needs. Like caching needs, what only information that they're caching is of, I think like the master, like the chunk server information on the client side, but the whole file caching, because it was the files are so huge, it didn't make sense to them to cache it. But in other distributed file system, it was written in that particular blog only that they cache files. I think they were talking about AWS there, but I don't know what AWS file system is. I have no idea about it. And
Yeah.
I got to know that they have a different distributed file system from that blog. I didn't know that. I thought they would be using something already which is there existing. But yeah, in there they cache the information. So this is the only thing I know. But if somebody has something else
Is
to
it
add on
Spanner?
top of it,
Is it Spanner by any chance?
Google Spanner? No, I
There's
didn't read
something
Google
called
Spanner.
Spanner, which
Spanner
is
is a database, like strong, consistent database. It's
Yeah,
not file system.
it uses those atomic locks or something, some different hardware.
Yeah.
Yeah. Mm.
I have another question. The master seems to have a huge amount of responsibilities, right?
Yes.
Yeah, it never becomes a bottleneck.
Yes, because one of the reasons is masters only responds to client with the chunk server information. Most of the operations are like read write operations. So that happens through chunk server. So there you don't need master at all. And once you have a chunk server information, You don't need master.
No, I see, but it also keeps track of which nodes are available, which had failed, and also rebalancing and moving data here and there, and also making decisions like where to replicate data, where to, I mean,
Yes.
it's a lot of things happening in background, right?
Yes. Yes.
And that's okay. It's okay to have just one master and it's capable of handling all that with no problem, or have they found some problems in this sense?
So they wanted to simplify the design. That's why they kept like this central master. The problems that could happen is like, you know, these are all background process. Some of them are background process, like, you know, garbage collection. It will only happen when the master is not busy at all. Like, you know, not busy at all. Like, you know, there are no requests coming. So now let me do garbage collection. So they have decided those scheduling on that basis, you know, like how
Okay.
free your master is. So I think that solves that problem. But yeah, this continuous heartbeat between master and this chunk server, this was a little overwhelming for me also, like, you know, because it needs to know every time, like the entire state of each chunk. But then I calculated, you know, it's not too much of information. It's fine, I think. And it can be kept in memory, and in memory operations are very fast.
Okay, right. That makes sense.
Yeah. Is there any other information on that? It support both read heavy and write heavy operations, or it's a read heavy?
It's read once and write once and read many times, or kind of operations are more common.
And more, so the callers for write operations are, you know, where it, if you know, you know, I know that I understood, like when it's a read many or it's a read heavy, then we can span a number of master that can support the read request. It is more or less an API call that where, and
Yeah.
it can also be done, I believe. But yeah, that's also an improvement. I mean, which is not definitely a part of this document, but I'm
Yes.
sure that, you know, Google would have encountered this problem and would have solved this.
I was thinking more of, you know, if there is one master, the things become easy to, like, it becomes more intuitive, like in the sense, you know, for example, I detect, you know, that, okay, this chunk server does not have a replica, this chunk does not have a replica, right? And at the same time, another master also detects the same thing. Now, me and that other master also have to be in sync, right? That, you know, both of us don't create replicas, you know. So that's why I think it makes sense here to simplify the system somehow.
Yeah, if so in a distributed system, right, you know, if you have any of those things where something is primary, something is secondary, that can easily become a bottleneck. And having one master, you know, it it reduces, or you know, going down and then bringing up the next master and all those things, it takes significant time. So your high availability and all that, those things probably might go for a toss.
Yeah, and I think that is a trade-off, right? Because they said they are okay with low latency. They are, what they want your system is to be fault tolerant and recover on its own. And I think that's the trade-off you have to do when you build your own application. That what you expect out of your system, right? But yeah, I think yeah, it depends on, like, you know, what your perspective is over here. Like, but I felt like, you know, this, because I think keeping, it's a trade-off, right? Either you have one master and take care of everything, or either you have multiple master. Now you have to sync those master also, and in those master also one master has to be a primary, because now how will you come to a consensus there?
Yeah, as soon as you introduce that, you know, the more things that you introduce where primary secondaries are there, that becomes a tough challenge, you know,
Yes,
to keep it
exactly.
in a distributed way. So if multiple nodes can do something, you know, the same kind of operation as much as possible, that makes it more distributed. Having primary, secondary, it, having more primary, secondary components, you know, defeat the purpose of a distributed system.
Yeah, but where you want consistency, you need to have someone take the charge and tell, like, you know, what you actually want in the end system. Like, you know,
Yeah.
here, like, if you want the data to be consistent, you need a primary, because like every node, if they're not talking to each other, and they just go with their own rights, the data could be very inconsistent.
That is not necessarily true in all the scenarios.
No, you need either you need a quorum, right, or you need a consensus.
Correct. So if we have a quorum, maybe quorum is a better way to have a primary secondary piece. A quorum gives you at least, you take away the primary secondary part.
But there are problems in quorum as well. Like, there are some sloppy things that happens at quorum. Like, obviously you'll be aware, but like, to point out, like, for example, you would be writing, because now there is no like leader or like, follower scene. Now everything is, is being written, and now you haven't reached quorum, and by that time somebody read from the quorum that has been already written, like from the node which has been already written, right? Now it has seen that inconsistent data where you didn't reach the quorum, and now you will roll back everything. So that again,
No, so in case of, I think we are going into a different discussion here.
Yeah,
No
it's a
doubt,
different
everybody.
discussion.
Yeah.
Yeah. So we are also at time. So yeah, you have anything to conclude, or like, are there any final questions? Okay.
Yeah, so thank you, Shreya, for sharing this. It was an amazing to see this Google file system. I didn't know anything about the Google file system, and it gave me good understanding about.
Yeah, thank you, Shreya.
Thank you.
Yeah, it was
Thank
a good
you.
session.
Yeah, thank you, Shreya. Actually, it was a good one.